Hi, this is a video where I'm going to be covering an AP chemistry video. I'm going to be covering 7.9, 7.10, and mainly 7.11, where we're going to get into electron configurations. So everything we've talked to prior to this has really been hydrogen, which is, I would call it a monoelectronic atom. It only has one electron. Now we're going to start talking about atoms, which most of them do have more than one electron. So polyelectronic atoms have more than one electron. I wanted to talk to you about hydrogen first. So the hydrogen with only the one electron, all of the orbitals of a particular n value. So what I'm talking about here is like if n equals 3, we have a 3s, a 3p, and a 3d. They all have the same energy, and this is only true for hydrogen. And what we say is that those orbitals are said to be degenerate. So degenerate, they're all going to have the same amount of energy if they have the same n, principal quantum number. But when you have an atom that has more than one electron, we'll think about this representation over here of sodium with 11 protons, and it has, let's assume it's just 11 electrons, that it's neutral. Actually, it could be an ion. I guess I say ion here. If let's just say it's sodium, sorry. The outermost electron here, this would be, if we think about the configuration of sodium, it's valence electrons are in the third level, so 3s1, there's one valence electron. That electron there's another 10 electrons in between. And these 10 core electrons are getting kind of in the way of that electron feeling the full charge of that positive nucleus. So that electron is not bound as tightly as some of the inner electrons are. And we say that that outer electron is being screened or shielded from the nucleus, feeling the full effect of the nucleus. So not only are those electrons in the way, they're also repelling each other, including that one electron, because they're all negative. Here we're going to start looking at what happens then when we do have more than one electron, these polyelectronic atoms. So we know that we don't know the electron exact pathways because of Heisenberg uncertainty principle. We can't know the location and the momentum of an electron at the same time. We know that electron repulsions can't really be calculated exactly, but we can make approximations. And the approximation that we use is when we treat each electron as if it were moving in a field of charge. That's a net result of the nuclear attraction or the average repulsions of all the other. So what I'm trying to show you is that when you have a polyelectronic atom, we're going to start talking about the fact that when n equals 3, these are not all equal in energy. They're not degenerate like they are for a hydrogen. So for a given principal quantum number, so let's say we're talking about the fourth n equals 4, the 4s orbital is going to have less energy than the 4p, which will have less than the 4d, and then that would be less than the 4f. So electrons are going to go into the orbitals in that order from low energy to high energy. They don't go exactly from 4s to 4p to 4d. We'll talk about that, but within n equals 4, they will fill in that order. So I want to talk about the penetration effect. This is really talking about whether the electrons can kind of penetrate or get through all those shielding electrons. So the more effectively the orbital allows it to do that, the lower in energy it is, and the more likely that the electrons are going to fill those lower energy orbitals that are able to penetrate towards the nucleus. So for example, like the 2s electron is going to penetrate the towards and get close to the nucleus, and spend a pretty significant amount of time, we think, near the nucleus. And it's gonna, at any given point, if you were gonna look at the probability, you can see that the 2s is going to have, 2 chances to be really close to the nucleus here, versus the 2p. So therefore, the 2s orbital, because it has this ability, is lower in energy than the 2p orbitals in that polyelectronic atom. So this is representing that probability distribution for an electron in a 3s orbital. It's mostly the electron's going to be found fairly far from the nucleus, but there is a small probability, but significant, that it will be found close to the nucleus. So the 3s electron is going to penetrate those shield of inner electrons. That's kind of what this diagram A is trying to show you. So there's a couple times where the electron could, based on probability, is going to be close to the nucleus. So if we look, then what results is that the 3s is going to be lower in energy than the 3p, than the 3d. So I definitely would recommend that you read that section. It's just kind of giving you some reasoning behind why we write our electron configurations the way we do in terms of energy. Now I want to talk about the history of the periodic table just briefly. Dmitry Mendeleev is usually the person that gets primary, credit kind of for starting to organize elements on the periodic table. And he was able to kind of lay out the elements, and there weren't that many known at that time. So he would leave spaces kind of for where the unknown elements, where he thought they would eventually be discovered. And then he predicted the properties of those, and he was pretty close. So, showing that this is there's patterns and repeating patterns within the elements. And that would have been, one of our first periodic tables. So this is showing you some of his comparisons, like for germanium compared to the actual once it was discovered in 1886. So you can see how close he was. So yeah, our current periodic table is based on atomic numbers. So if you look at our table, it goes from atomic number 1 to 2 to 3 to 4. It's really counting by atomic numbers and not the atomic mass. So if you look at the periodic table carefully, you'll see if it were to go by mass, it would have been a little bit different. In fact, like argon and potassium would have been in switch spots, and that would not have made sense because potassium violently reacts with water. It's not a noble gas. It's so it would not fit, chemically into that noble gas group. Similarly, the argon is very unreactive and it wouldn't fit very well with the alkali metals. So now I'm going to talk about the periodic table in terms of the electron configurations. First, we're going to talk about Aufbau's principle. So as there's protons being added as we go through the periodic table, electrons are also added. And that, they're going to be filled from lower to higher energy. So the word Aufbau is German for building up. So you can see boron has 5 electrons, and they're going to start at the lowest energy, and then they'll go filling, going up. This would be a ground state electron configuration for boron, where the electrons are as close as possible to the nucleus. Hund's rule, this is kind of showing you Hund's rule. In honors, we used to say it was the bus rule. The electrons go into the orbitals singly, spinning in the same direction before doubling up. The way that it's worded here is the lowest energy electron configuration is one where you have the maximum number of unpaired electrons. So you do eventually have to double them up and then use Pauli exclusion principle, but electrons are going to, each enter their own orbital, and they're much more energetically stable by doing that. The periodic table, you can think of it in terms of blocks. The group 1 and 2 are the S block. The groups 3 through 12, our numbering system on ours is different than this one, but 3, 4, 5, 6 through 12, those are what we call the D block. They're all, those elements are in the process of filling the D orbitals. And then when we get over to the red here, we're in the P block. So they're all in the midst of putting electrons into the P orbitals. And then at the bottom, we have what we call the F block. The number n and n-1 and n-2, that refers to the period, which is also the principal energy level. So we, if we are an element right here, that element is going to have electrons in the 5s orbital. And that's because I'm in the 5th period. Whereas when I'm in the D block, you can see these are 1 less than what the n value is. So this period is n equals 4, but these are 3D electrons that are filling the orbitals in the 3rd energy level. And then we pop out here and we're going to be again n. So if I were in that same period, and let's say this is the element I'm talking about, the outer valence electrons are going to be 4s2, 4p4. When we get to the F, we actually drop down 2 from whatever the n value is, and the F's appear right after right here. So when you get to that point, you go down, and we're in n equals 6, but these are really the 4 F's. And then if you're here, you drop down, and then it's n-2 would be 5, so the 5 F's. So let's look at your periodic table. You don't necessarily need to label it, but just realize that we can kind of label, just reminding you on how we did this in honors. It's a little different when we deal with the F block, and we will deal with that soon enough. But I want to do some examples with you. These are on the note sheet if you want to do those with me. So the first example I'm going to do is sulfur. And sulfur's right here. I'm going to write the electron configuration by essentially, like I'm reading a book, left to right, top to bottom. So I would write down 1s2. So I know my first 2 electrons are going to go in the first energy level in the S sublevel. Then I would read right here, and I would say 2s2. Then I come across, remember this is still n, so 2p6. Then I come here, 3s2. Then I come across, and I count 1, 2, 3, 4, so 3p4. I can also use noble gas electron configuration. This is not that long of an electron configuration, but it's nice to know how to do it. And what you do is you choose the noble gas that has a lower atomic number than the element you're trying to write. So for sulfur, we would have picked neon. And then instead of writing this whole part, we can just write brackets around neon, and that represents those electrons, and then 3s2, 3p4. So will find that those are nice and convenient to do, so you don't have to write so much. So let's do a few more and see some other things that happen with these electron configurations. Some of this is going to be a little different than what you've learned in honors chemistry. So let's do barium. So barium is right over here. And you can try it and pause the video and see how you do. I am going to write it with noble gas configuration. So I'm going to start with xenon. So I'm doing barium. I'm going to write xenon. And then I'm going to come around and n equals 6. So 6s2. Now I'm going to do nickel. And nickel, let's do just the plain nickel, and then we're going to do the ion. So let's, again, if you want to pause and try this one, I'm going to do the noble gas. So I'm going to pick argon. And then I'm going to read from there. So before S2, then I drop down. Remember, this is n-1. So now I'm in a 3D. And it would be 3D 1, 2, 3, 4, 5, 6, 7, 8. So that's nickel. But if nickel were nickel plus 2, the ion, that means there's going to be 2 electrons that are lost. The electrons that are going to be lost are always going to be the s electrons first. So we're going to get rid of these 2 electrons. So the nickel plus 2 ion would have an electron configuration of argon and then 3d8. Let's do a different one now. Let's do, we're going to do europium, which is down here. So atomic number is 63. So the noble gas, assuming I want to write noble gas configuration, which I am going to, I'm going to use xenon because it has the closest but lower atomic number to the one I'm writing. So I'm going to write down xenon to represent all those electrons up until xenon. And then I'm going to start here and I'm going to write 6s2. And then now, if you can see, it goes 57 through 71. So I'm going to come down here, and what you're going to see is that the first element is really D1. So that would have been, this D is going to be n-1. So it's going to be 5d1. So 1 electron will go into the d orbitals, and then it will, the electrons will start filling into the F. And the first F orbital is this element. And then there's 14 of them. But we're going to the europium. So it'd be F1, 2, 3, 4, 5, 6. So it would be 4F6. So you only need to write the D if it is in the process of filling and ending. The electron configuration will end in the F block. Let's try titanium, and then we'll do the ion. So titanium is right here. So again, I'm going to do the noble gas configuration. And I'm going to pick argon. And then I'm going to write 4s2. And then I'm dropping down, so 3d2. And titanium, if this is just titanium neutral, but if I were going to do titanium ion plus 1, then one of the s electrons is going to be given away. So it would be 4s1, 3d2. You can also write that as Whoops. Yeah, that's right. Sorry. So I'm going to write it. I'm sorry, losing my track. Yeah, I'm going to leave it like that. So one of the s electrons is going to be lost. You could possibly, this one extra electron then could go into the D. So it could be 3d3. And so then the s orbital is not there anymore. So you could do either one. So when we have transition metals, we can count those d electrons towards the valence electrons, and it is possible for those to be lost along with the s electrons that come before it. The last one I wanted, or one of the last things I want to cover with you are elements where the d block or the d orbitals are either really close to being half full, which is right here, these elements. So let me show you this. So if we were going to write the electron configuration the way that we were taught, in honors, we would write, if we're going to do chromium, we would write it as argon, 4s2, and then 3d4. And what you need to do is realize, so these are my d orbitals. There's 5 d orbitals. And I have those 4 electrons. And it's particularly stable if it can have a completely half full set of 3 or any d orbital. So what'll happen is one of these s electrons will be promoted into the d. So what does that mean? It means it'll be electron configuration of argon 4s1, because one of them went so that the 3d orbitals could be half full because it's energetically favorable. Similarly, this very similar happens when you're talking about the d orbitals being almost full. So now I'm talking about the copper and silver and gold. Let's do copper. So we would write copper the way we were taught. Copper is going to be argon 4s2 3d9. So we're really close. Again, you don't have to write it, but sometimes it helps to visualize. So 3d9 is really close to having that full set of d orbitals. So what's going to happen is one of these s electrons is going to go into the d. So what you're really going to get for copper is argon 4s1 3d10. So let's do a couple more. Let's do some that'll be kind of more similar to some of the WebAssign. We're going to do the noble gas electron configuration for nihonium, which is right here. So if we do the noble gas configuration for that one, we're going to pick radon. And then 7s2, so we're right here. Don't forget, we do need to go down. This time we don't need to write the D1. It would be 6D1 and then 5F14. But we're just going to right away write the 5F14 because we're going to go back up and fill the D. So then we're going to have 6D10. And then we come out to n equals 1 in the P block, so it would be 7P1. So if you're going to go entirely through the F block, you don't need to write down that D1. Let's do another one. Now we're going to do platinum. And let me find platinum. Platinum. is somewhere right here. So for this one, it's pretty straightforward. So we're going to have xenon be our noble gas, 6s2. And then we have to go through the F's again. Like I said, no need to write down the D unless we end in the F's. Then we come back out, and then we are going to have, the 4F14, then 5D. I'm doing the wrong one. Sorry, we're doing platinum. So 6s2, 4F14, then we come back out, 5D8. So there might be questions like, well, how many valence electrons does this have? I would go, sometimes we do include those d electrons. For sure it has these two. I would go with 2 probably for this problem. And then the valence electron notation, if they ask us, would just be 6s2 for that question. Let's talk about valence electrons. We've already been kind of using them, are the outermost principal quantum level electrons, which are typically S and P, but can include the D when you're in the transition metals. But in the transition metals, if they're going to lose electrons, they typically lose the S first. They're more on the exterior of the atom in that orbital than they are for the D. The core electrons are all the electrons in the inside that are not valence electrons. So for groups 1, the way our periodic table is labeled, it's actually groups 1, 2, 13 through 18. These are the representative elements, and we're going to have valence electrons of 1, 2, and then these are the ones where you'd minus 10. So you'd have 3, 4 through 8. But like I said, the osmium, this is a transition metal. This is the electron configuration. It has 2 valence electrons, but up to 8. So it might lose 2, and if it does and becomes osmium plus 2, then these electrons are going to be lost. But maybe it's going to become plus 3. Then it would be xenon 4F14, 5D5, and that might be more stable because now it has that half full D orbitals. So valence electrons, if you don't already know this, you might want to add this to your periodic table. So this is what I was just saying, but now we can put it on our periodic table. So 8, helium just has 2, but everyone else in group 18 has 8. Special names for groups. We do talk about these quite a bit. So group 1, for us, not A, we have a different numbering system, but group 1 we call the alkali metals. Group 2 are the alkaline earth metals. And then this is really group 3, 4, and so on. This is 13, 14. Halogens are 17, and the noble gases are 18. Transition metals are what we call also the D block. They're in the midst of filling the D orbitals. And then the F block we can call the lanthanides. It's the first row of the 4F. And then the actinides would be the second row, the 5Fs. So we just did those questions. And we covered all that, but let me see. There's one more, this question. So everything we've done so far have been ground state, where the electrons are in the lowest possible energy levels, other than those exceptions where the 4s electrons gets promoted to the D. But here we can just kind of look at these and decide whether they're ground or excited. So this first one, this one is excited, because it should go 1s2, 2s2, 2p1. So it skipped the p, the 2p's and the 3s. So the electrons are excited, they gained energy, and they're at a higher energy orbitals. This one, letter B, is not excited. Letter C, that one, because this isn't filled, it should have been 2p5 before it went to the S, so this one is excited. And then this one, argon, and then 4s2, this should have been filled before going to the P, so this is also electrons that are higher in energy than they are when they're in ground state. How many unpaired electrons are there in each of those up above? So you can, visualize this if you want. So letter A, there's going to be that 1. Letter B, there's going to be none. Letter C, there'll be 1 in the 3s. Oops, there might be more. I have to think, because we have the 2p that's not full. Okay, so this one actually has, I'll move the 3s over here. So this is C, and there are 3 unpaired electrons right here. And letter D, I'm going to have the 3d5. So 1, 2, 3, 4, 5, and then 4p1. So there's a lot of unpaired electrons there. So there's going to be 6. So I think we just covered everything here. We never identified what element it is. So when we were doing this, we could easily, assuming it's an atom and not an ion, we can count the electrons. Like there's 5 electrons there, so I know that that's boron, but it's an excited state of boron. This one here, there are 10 electrons. This is neon. This one, there are 9 electrons, so this is fluorine. And this one, there's argon, has 18 plus 8 more, I think 7. So then we're going to have 26, and that would be iron. Paramagnetic and diamagnetic, when you look at those unpaired electrons, if there are any that are unpaired, we say that they are paramagnetic. They're going to be attracted to a magnetic field. And if you look back at our examples up here, we would say this is paramagnetic because it has unpaired electrons. All, A, C, and D are all paramagnetic, and letter B would be diamagnetic. So just covering those terms, just because you'll see that in the Web of Science. So if the electrons are all paired, there's no magnetic ability, and if some of them are unpaired, they will be attracted to a magnetic field, but then they'll lose their magnetism when you remove them from the magnetic field because they have those unpaired electrons. So that is all I have. I hope that helps. If you have any questions, don't hesitate to ask during class.